Friends, very good morning everyone. We were dealing with various reactions of phenols. We have seen that it undergo electrophilic substitution reaction more easily. It is attributed to the fact that OH is an electron donating group. Hence, it donates the electrons and activates the ring system. That's why the electrophilic substitution reactions are more easy. You have seen about nitration, sulfonation, halogenation, and so on and so forth. As these phenols are activated system, it can also undergo reaction with the electrophiles which are very weak or they are not very strong. Nitrization is one reaction which is exhibited by phenols but not by benzene. This is because of the OH group, the activating group present in the benzene ring system. Phenols reacts with nitrous acid to give para-nitrosophenol. Here nitrous acid reacts with phenol to give rise to para-nitrosophenol. This electrophilic aromatic substitution occurs only in phenols and with a weak electrophile NO+. If I take orthohydroxytoluene or orthomethylphenol and treat with sodium nitrite and HCl, it gives rise to para-nitrosophenol. Let us look into the mechanism of the reaction. We know that sodium nitrite and HCl reacts to give rise to nitrous acid. And we have seen this reaction in the preparation of benzene diazonium chloride. Phenol has lone pair of electrons on its oxygen. This is donated by the OH group to the benzene ring system. When these electrons are donated, this forms a double bond and this carbon has to maintain its tetravalency. That's why these 5 electrons will be kicked off to the next position. Once this electrons moves, this becomes more electron rich and it has to maintain its valency. Pi electrons moves on to the para position and this will give rise to a carbon ion at the para position. Nitrogen is positive as it is attached with an electronegative oxygen. Carbon ion electrons attacks onto this nitrogen and OH gets kicked off. And it gives rise to corresponding nitroso group attached to the para position. It is unstable because it is not aromatic. It regains its aromaticity by loss of these hydrogens. The carbon-hydrogen bond breaks and this electrons forms the bond over here. As the carbon become electron rich, it has to maintain its valency. That electrons are moved to the next position and the pi electrons moves onto the oxygen and O minus it combines with this H plus and it gives rise to para-nitrosophenol. This is the mechanism involved in the nitrization of the reaction. Though nitroso group is very weak, but still it can react with phenol because phenol is more active. Another reaction which is shown by phenol is coupling reaction with diazonium salt. Here, the diazonium chloride is also a weak electrophile. Phenol reacts with benzene diazonium chloride to give azo derivative. These azo derivatives are used as dyes. That's why these are come under the category of azo dyes. Azo dyes are used for its coloring of the textiles and clothing, etc. How this reaction occurs? Let us look into it. The mechanism involves here like this. If I take a phenol, the lone pair of electrons on the oxygen is donated to benzene ring system, which forms the double bond, and this carbon has to maintain its tetravalency. Pi electrons moves on to the next position. Once these electrons moves over here, the carbon becomes electron rich and a carbon ion is generated. This reacts with benzene diazonium chloride. This is the positive center. To satisfy this positive center, pi electrons moves to the next position. Once these electrons moves, the carbon ion electrons attack on this nitrogen, which becomes positive, and it gives rise to corresponding diazo derivative. This molecule is unstable because it is not aromatic. It regains aromaticity and becomes stable. The carbon hydrogen bond breaks. These electrons are utilized to form the double bond. Once the double bond is formed here, this carbon becomes rich and it has to maintain its valency for its stability. That's why pi electrons moves onto the oxygen. O minus, it combines with this H plus and it gives rise to corresponding ortho-aza derivative. This is another unique reaction which is given by phenols but not by plain benzene ring system. It undergoes one more reaction that is given by Kolb's. That's why it is named after him as Kolb's reaction. It is essentially a carbonation of phenol. Carbonation means we are adding CO2. Sodium phenoxide reacts with carbon dioxide at 125 degrees centigrade and 4 to 7 atmospheric pressure to give sodium salicylate, which upon hydrolysis gives salicylic acid. Kolb's reaction is of synthetic importance because it is used to prepare salicylic acid, which serves as a starting material for the preparation of aspirin, a analgesic drug. Like nitroso group, like diazonium group, carbon dioxide is also a weak electrophile. And this carbon dioxide weak electrophile do not react with benzene, but it reacts with phenols. That's the beauty of phenols. Because it is more electron rich, it is more activated, that's why it can react with the weak electrophiles also. Let us look into the mechanism of this reaction. Sodium phenoxide O minus Na plus. The excess electrons on this O minus is donated to benzene ring system. The carbon has to maintain its tetravalency for its stability. Thus, the pi electrons on it is moved on to the next carbon, generating a carbene ion. The carbene ion which is formed reacts with carbon dioxide. The carbene ion which is formed reacts with the carbonyl carbon. This is the positive center as it is flanked with two oxygens which are more electronegative than the carbon. The bond between the carbene ion and an electron deficient center forms. It has to maintain its tetravalency for its stability. Pi electrons moves on to the oxygen, giving rise to corresponding C double bond O minus. This molecule or an intermediate, it is unstable as it is not aromatic. It regains its aromaticity by losing these hydrogens. The carbon-hydrogen bond breaks and these electrons are utilized to form the bond over here. The carbon is electron rich, pi electrons moves on to the oxygen, O minus, it combines with H plus and it gives rise to corresponding salicylic acid. Kolb's given this reaction and this is named after him in his remembrance. Another reaction which is very unique to phenols is Remer-Tiemann reaction. In Remer-Tiemann reaction, phenols reacts with chloroform in the presence of aqueous sodium hydroxide at 70 degrees temperature, followed by hydrolysis with acid gives corresponding salicylaldehyde. In Kolb's reaction, we have seen we got salicylic acid, that is orthohydroxybenzoic acid. Here, this gives salicylaldehyde. The salicylaldehyde can also be oxidized to salicylic acid, and this serves as a starting material for preparation of many compounds of drug quality. Remer-Tiemann reaction is also an unique reaction. Why is it? We will look into it. What is uniqueness in this? What are its salient features? Let us look into its mechanism and let us know it. Here, chloroform CHCl3 reacts with potassium hydroxide or sodium hydroxide, OH minus, which is electron rich. It abstracts the proton from the chloroform. The carbon in chloroform is electron deficient, as these three chlorine groups are electronegative in nature, which pulls the electrons towards itself, rendering this carbon electron deficient. With less number of electrons, it is holding this hydrogen. That's why the carbon hydrogen bond in chloroform is weak. As it is weak bond, it is easy to break. In other words, chloroform is acidic enough to give the proton, and hydroxide ions are basic enough to accept the proton. OH minus abstract this proton, leaving its electron pair onto the carbon. A carbene ion is generated. Then the chlorine, along with its electron pair, it moves away and it gives rise to dichlorocarbene. This dichlorocarbene is electron deficient carbon. It is neutral in nature. The carbene is then intermediate formed in this reaction. These carbenes are electron deficient neutral carbon. In case of carbocations, the other intermediate which we have come across in the other reactions, they are electron deficient carbon like carbenes, but they are positively charged. Here, this carbene is electron deficient but neutral in nature. That's the difference between carbocation and carbene. Carbene is an intermediate formed in this reaction. This is the salient feature of Remer-Tiemann reaction. This carbene, as it is an intermediate, it is highly reactive species and highly unstable species. Carbene immediately it reacts with phenol. OH in the phenol reacts with the dichlorocarbene. The pi electrons moves onto the ortho position, giving rise to a carbene ion. The carbene ion donates its electrons to the carbene. It is neutral in nature. The electrons are donated to the carbene. Once it donates the electron, it becomes electron rich. I get CH3Cl2 attached to the carbon at the ortho position. As the electrons are gained by carbene, it becomes carbene ion. Carbene ion which is formed combines with H plus and it gives rise to corresponding CHCl2 group over here. Then this compound undergo hydrolysis OH minus attack on this positive center. This is positive center because it has two electron withdrawing groups attached to it. OH minus attacks over it. It is already having 4 bonds and it has to maintain its tetravalency for its stability, and already bond has been found between carbon and OH, and it is strong bond, and OH is not an easy living group. Chlorine, as it is an easy living group, it kicks off chlorine to maintain its tetravalency. Then it gives rise to corresponding hydroxy group attached to this carbon. This bond, the electrons of the OH bond breaks, and this forms the bond with carbon, and it has to maintain its tetravalency, and chlorine gets kicked off, and it gives rise to this H plus and Cl minus. They combine together to lose as HCl, and it gives rise to salicylaldehyde group. Aldehydic group attached to this ortho position. It regains its aromaticity for its stability. Carbon-hydrogen bond breaks. Electrons moves towards the benzene ring system. The pi electrons moves onto oxygen, and this O minus combines with H plus, and it gives rise to corresponding salicylaldehyde. The Reamer-Tiemann reaction is unique because an intermediate carbene is formed which is not seen in any of the reactions. This carbene generation mechanism was found out by Reamer and Tiemann, and that's why it is named after them in the remembrance of them. These are the other few reactions, that is Kolb's condensation, Reamer-Tiemann reaction, nitrization, and diazo coupling. These are the other 4 reactions which are given by phenols but not by benzenes. This is attributed to the OH groups attached to the phenol ring system. Here, the OH group is activating the ring system. We can do better work or better things when we have a better support from the organization where we work. Hence, we should always work with the organization which supports us, or in other words, which activate us, and we can do much more better work. That's why always stay with the organization which is activating you. If you stay with a deactivating organization, we also become deactivated. This is the message of phenols, that we always should stay with a organization which activates us. This is all about the reactions of phenols. Next class, next session, we can meet with a new chapter. Thank you.